start talking? Yeah. Good afternoon, or morning, or evening, depending on your geographical location or where you are now. It is my pleasure to give this talk on the frequency domain methods in sliding mode control. Let me introduce myself. My name is Igor Boiko, and I'm a professor with electrical engineering and computer science department of Khalifa University, Abu Dhabi. This subject of our talk is quite specialized, and I believe that the audience familiar with sliding mode control. And maybe what I'm going to talk about would provide a slightly different perspective on the subject, because normally the analysis of sliding mode control is done in the state space domain, and we are going to take a look at this phenomenon from the perspective of frequency domain analysis. And the methods that I'm going to consider in this talk start from the classical describing function method and harmonic balance principle, and proceed to the methods that I would label as new, which are phase deficit and the locus of a perturbed Belay system. The describing, let us recall what the describing function method is. So first of all, it is applied to a nonlinear system in which the nonlinearity can be separated from the linear part from the rest of the system, from the usually the dynamic part of the system, and it is based on the assumption that the input to the nonlinearity, which is x here, is a sinusoidal function. Of course, because we have a nonlinear function, the signal y here, the variable y, will be non-sinusoidal, but z again can be quite similar to a sinusoid signal if the transfer function w of s has low pass filtering properties. In this case, z can be also quite close to a harmonic signal. And in this case, we can simply ignore the fact that the signal y has is not a sinusoidal signal, is not a harmonic signal, because all high harmonics might be, under certain conditions, filtered out by the linear part of the system. And in the describing function analysis, we essentially track or trace the propagation of the first harmonic in the signal. And the describing function is simply a complex gain, which of the complex equivalent gain of the nonlinearity, which describes propagation of this harmonic signal through the nonlinearity in terms of the first harmonic in the output signal from the nonlinearity. We know that because the output of the nonlinearity is a periodic signal, we can represent it as a Fourier series with those coefficients that are given here. So it's an infinite series, and the coefficients are given by those intervals. And if we simply disregard all high harmonics, and we can write for the signal y that it is approximately equal to a certain constant or biasing term plus the harmonic signal a1 by cosine plus b1 by sine of the signal, then we can consider the describing function which will describe the propagation of this first harmonic. And approximately the output signal from the nonlinearity can be considered as n of a, where n is the describing function, multiplied by the input signal. By doing this, we replace the nonlinearity by a linear coefficient, which is complex in the general case. However, it retains the nonlinear dependence on the amplitude. It's not a constant coefficient. It depends on the amplitude of the input signal. And we write it as the sum of the real part and the imaginary part, Q and Q prime. And Q and Q prime are obtained from the coefficients of the Fourier series, B1 and A1. We simply divide those coefficients by the amplitude A. We can also view the describing function in a sense as an average slope of the nonlinearity on the interval from 0 to A, where A is the amplitude of the harmonic input signal. So now, if we consider a closed loop system where signal X is a negative output of the system Z, and we know that oscillations can be excited in this system, self-excited, non-vanishing oscillations. And these non-vanishing self-exciting oscillations can be found through the use of the harmonic balance principle. We can simply trace those signals X as a result, or as a negative Z, Y is a result of the propagation through the nonlinear X multiplied by the describing function in this case, and Z is a result of the propagation of Y through the transfer function W of S. So if we write these equations, we can derive the harmonic balance condition or the harmonic balance principle, which states that the product of the describing function at the at the amplitude of the oscillation by the frequency response of the linear part at the frequency oscillation must give -1. So now if we divide both parts of these equations by n of A, we can rewrite this harmonic balance condition as W is equal to the quantity that we will be referring to as negative reciprocal of the describing function. This is a form which is very convenient for the graphical illustration and for determining if the oscillations may happen in this system, because we can simply depict the solution of this equation in the complex plane. On the one hand, we can draw W, which will be the Nyquist plot, and on the other hand, we can draw negative reciprocal of the describing function as a function of A. And if they have a point of intersection, then this point of intersection is the solution of the harmonic balance equation, and we have the frequency and the amplitude of the oscillations. The harmonic balance condition we can also note is a complex equation, and we can represent it as two equations. The condition, the balance condition for the amplitudes, and we will call it the amplitude or magnitude balance condition, and the phase balance condition. And I draw your attention especially to the phase balance condition, so that we need to have the phase balance, so that the phase of the describing function plus phase of the linear part of the Planck transfer function must give us -pi. Only under those conditions we will have finite frequency oscillations in this system. So what is the relationship of all this with the sliding mode control? Sliding mode control is usually or very often realized as a relay control, which is given by the second formula here. And in this case, the plant is given by those linear equations with state in the state space. And sigma here is the sliding variable, which is defined as the weighted sum of all the states of the system. So S is the raw matrix containing all the coefficients of the sliding surface, essentially defining the sliding surface. And the sliding surface would be given by the equality of sigma to 0, or Sx equal to 0. The describing function of the ideal relay is given by the well-known formula n is equal to 4c over pi a, where c is the amplitude of the relay and a is the amplitude of the oscillations at the input to this nonlinearity. So what would it look like? What would this solution look like for a sliding mode control system or a relay feedback system in a general case? So the describing function of the relay was given in the previous slide, and this is only a real quantity, it doesn't have an imaginary part. As a result, the negative reciprocal of this is this blue line, which is drawn along the real axis in the complex plane. So this is the negative reciprocal of the describing function of the ideal relay. And here we have three different frequency responses, or three different Nyquist plots corresponding to three different cases. This dashed line corresponds to the first order linear system, and dotted and solid lines correspond to the third order linear systems. You can see that the dotted line doesn't have any point of intersection with this blue line except the origin, and dotted and solid lines have those points of intersection with this blue line, which give us frequency and amplitude of the oscillations. And for the sliding mode control systems, that would constitute chattering in the sliding mode control system. So it's the system for which the linear part is represented by the dashed line doesn't produce chattering, and the systems that are represented by dotted or solid lines would produce chattering. And the difference between them is the order of the linear part, or the relative degree of the linear part. That would be also similar. So first order or first relative degree, or third order or third relative degree. If the relative degree is 1, then ideal sliding mode occurs. If the relative degree is 3, for example here, or higher, then the chattering occurs in this system. So, and this is the idea behind the analysis of chattering here. Now, let us consider also the describing function of the hysteresis relay, which will be instrumental later. If we have a hysteresis relay, for this relay, the describing function is given by the following expression. So now we have an imaginary part also, a real part and imaginary part also. And if we find the negative reciprocal of the describing function for this hysteresis nonlinearity and write it as the harmonic balance equation, we will obtain the following formula. So we have the Nyquist plot of frequency response on the one hand, and the negative reciprocal of the describing function on the other hand. And what is remarkable here is that the negative reciprocal of the describing function has the imaginary part, which is given here, which doesn't depend on the amplitude of the oscillations, which doesn't depend on A. It depends only on B and C, where B is the hysteresis value of the relay and C is the amplitude of the relay. So for a given relay, the imaginary part is constant, and as a result, the negative reciprocal of the describing function is just a straight line parallel to the horizontal straight line, which is located below the real axis at the distance of pi b over 4c. And all the systems that we considered above would have a point of intersection with this line, and as a result would have the system would exhibit chattering. So this is also what we need to know. Describing function analysis can also be used and very, let's say, convenient for analysis of high-order sliding mode control too. For example, if we consider two-relay controller or the twisting algorithm, so if we talk about twisting algorithm, I should, if we talk about sliding mode control, I should probably talk about twisting, because two-relay control is a kind of extension to that, to the twisting algorithm. For the twisting algorithm, we must have, so in the original formulation, the relative degree 2 from the control U to the output of the system Y. So it's between U and Y, we must have relative degree 2. And the twisting algorithm is given by the following equation. It is a sum of two relay controls, a signum of Y and signum of Y dot. And if we apply describing function analysis to this algorithm, just simply assuming that Y is a sinusoidal signal, and we know what the describing function expression for this relay and for this relay, so we can find the describing function as a sum of two describing functions, and consider also the relationship between the amplitude of Y and amplitude of Y dot, which is through omega. So we now can come up with this expression for the describing function of the twisting algorithm, which is given here. And now, if we consider the negative reciprocal of the twisting algorithm, we find we derive this equation. And we can see that the ratio of the imaginary part and the real part is constant. That means that the negative reciprocal of the twisting algorithm is simply a straight line, which is shown here in this plot. And it has the slope. It has the slope which is given by arctangent of the ratio C2 over C1. C2 over C1. So again, if our Nyquist plot of the plant intersects this negative reciprocal of the describing function of the controller, we have chattering in the system, which we have a solution, a periodic solution. We can find omega and A of these oscillations, and this would constitute chattering. If we don't have a point of intersection, which would happen if our linear part has relative degree 1, then it would go in this quadrant, or 2, that it would go only, the high frequency would be in the third quadrant, then we wouldn't have a point of intersection. We would have an ideal sliding mode in this system. And now I'm going to introduce a new concept, the concept of phase deficit. What happened? So we find that if we have a point of intersection between the negative reciprocal of the describing function and the frequency response or the Nyquist plot, then we will have a periodic solution or chattering. What happens if we don't have this point of intersection? It is remarkable that now the motions in the system would depend on the angle between negative reciprocal of the describing function or its low amplitude asymptote and the high frequency asymptote of the Nyquist plot. So the higher this angle would be, the faster this convergence would be. The faster this convergence would be, and the convergence would always be finite time if this angle is positive. So this angle is what was named as phase deficit. Phase deficit. So phase deficit, mathematically it is defined here as pi plus this limit of the describing function plus this limit of the frequency response. And it was proved that the origin in the state space can only be locally asymptotically stable if the value of the phase deficit is non-negative. It can be either 0, and in this case we will have asymptotic or infinite time convergence, or it can be positive. In this case we will have finite time convergence. So here there are a few options that illustrate this notion. For example, we have two Nyquist plots, W1 and W2, and two negative reciprocal describing functions, N1 and N2. If we have W1 and N1, the phase deficit is 0, and we have infinite time convergence to 0 of the motions in the system. If we have W1 and N2, we have finite time convergence of the motions in the system. If we have W1 with N1 or with N2, we have a negative value of the phase deficit and or respectively points of intersection with N1 and N2, and we will not have convergence at all. In this case, we will have finite frequency oscillations or chattering in the sliding mode control system, and respectively the origin in the state space will not be stable at all. So we don't have a stability of the origin at all. So we have oscillations in the vicinity of the origin and not the stability of the origin itself. Respectively, for the twisting algorithm, we can see that the phase deficit is always positive if we have positive value of C2 and C1, and we will always have finite time convergence, of course, if our W is of relative, corresponds to the relative degree 2 of the plant. And now I'm going to consider one more concept. I'm leading to the method which is called LPRS, or the locus of perturbed relay system, and some foundation principles of that are given here. First of all, we are going to consider the effect of propagation of external signals now through a relay feedback system, using the concepts of the describing function method. So let's assume that now our input to the nonlinearity has a biasing term, which is given here by sigma 0. Sigma 0 is a constant value. So sigma is a constant plus a sinusoid. And the output of the relay will be given here as those switches of the ideal relay. The switching happens once sigma crosses 0 at this point and at that point. So at those 2 points we have switches of the relay. Now what we are going to consider is the averaged value of the output of the relay, or the averaged control, so which is labeled here as U0. And of course it is given through this integral, or geometrically it is the difference between those two areas, between the red area and blue area in this figure. So this is what corresponds to U0. As before, we can find the describing function here, describing function even for a biased sinusoid. And here we have propagation, which is this figure illustrates the propagation of the sinusoid through a hysteresis relay. So we have switches of the relay when sigma reaches the values, crosses the values of minus b and b, where b is the value of the hysteresis. Here we have the describing function. And now we would like to obtain the bias function. Bias function is the dependence of U0 on sigma 0 at a certain given value of the amplitude A. And the bias function is shown here by this plot. Basically, it's an arc sine function for a relay nonlinearity. What would also be interesting here is what the slope of this bias function would be at the origin, at the point of origin. And this slope is found by differentiating the bias function with respect to sigma 0, and it is given by this formula, and we will call it equivalent gain of the relay. So this is the equivalent gain. So here we have some certain family of the bias functions, drawn here for different values of the hysteresis in the system. Also, what is worth noting is that for the ideal relay, Kn is simply C is the amplitude of the relay. And if we recall what n of A is, n of A was 4c over pi A. So Kn is exactly just half of n of A. And because Kn describes, or we will be using it for describing the propagation of external signals, or for describing the dynamics of averaged motions in the system. So the dynamics of the system that describes the average motions inherently has the stability, gain stability margin of 2. And we can say that this system, the relay system, has the inherent gain stability margin of 2 for the averaged motions. Now we can use this equivalent gain for the analysis of the propagation of external signals through the relay system. And it is done on the basis of the following assumptions. we will assume, of course it's not quite true, but approximately it is fulfilled, that the amplitude and frequency of the oscillations do not change when an external biasing signal is applied, that the bias function is close to a linear function, and that the external signals that cause bias in the oscillations are slow in comparison with the self-excited oscillations. Usually all these assumptions approximately hold. And as a result, the dynamics of the averaged motions in the system can be described by a linear model, which is obtained by simply replacing the relay nonlinearity with the equivalent gain. So we simply replace the relay, which is, or the nonlinearity, which is f of x here, with the equivalent gain, and this would be our dynamics for the averaged motions in the system. And now about the locus of a perturbed relay system. So I will very briefly go through the concepts of the LPRS method because it may be a subject of consideration just by itself. So if we have a relay control through a feedback through a hysteresis relay and a linear path, which is given here, we can figure out that the input to the relay, which is sigma, error signal, causes those switchings of the relay at the times when the sigma becomes equal to minus b or b. Then let us recall what the describing function was for the hysteresis relay. It is given here. And here it is the equivalent gain for the hysteresis relay. Now, if we write this harmonic balance equation, the hysteresis for the hysteresis relay, which is given here, what we can notice here that this part in the real part, which I'm trying to indicate here, is exactly what is given in the Kn. So this is the reciprocal value of the Kn. As a result, we can rewrite the harmonic balance equation in the following way. And we also replace the value of b here in the imaginary part with negative y at 0, at time 0, because at time 0, the signal y must be equal to b, and this causes the switch of the relay from minus to plus. So this is our certain transformed harmonic balance equation. And what we're trying to do with the LPRS, we're trying to define a function that would replicate this definition, replicate this right-hand side of this formula, but in which the quantities of Kn and y at time 0 would be fulfilled exactly. So because the harmonic balance is an approximate method, we're trying to design a method which would be exact. So this is a definition, this is some definition, or this is the formula that leads to this definition. So we define LPRS, locus of a perturbed relay system, as the following formula, as the following dependence, in which the omega is varied by varying the value of the hysteresis b. So if we somehow manage to compute this function, we will be able to do what? We will be able to, through finding a point of intersection of this function with this straight line, which is pi b over 4c, to find the omega, the frequency of chattering exactly, and the equivalent gain through this value of the real part at this point of intersection, because it's half of the reciprocal value of the equivalent gain. So now I'm without explanation briefly go through the technique of computing the LPRS. We start from this solution in the state space, and we write the return Poincare map, and then we find or use the formulas for the closed loop system, and find the quantities that we need for the formula by which we define the LPRS. I'm just skipping all this. And as a result, we will arrive at this formula of the LPRS. You can see that this is a function G, is a function of frequency, and it includes only the matrices of the original system, matrices A, B, and C. It doesn't include any values from the nonlinearity or the quantities that we used in the definition. So essentially, this is a function of the linear part or of the plant only. And of course, it includes omega as the variable that we change, independent variable. So in a sense, like the frequency response or the Nyquist plot describes the response of the linear system to harmonic excitation, LPRS, which is given here, describes the response of a linear system to square pulse excitation. And this square pulse excitation has infinitesimally small asymmetry, through which we would also like to see how the average signals propagate through these dynamics. The relationship between the LPRS and the Nyquist plot can be also highlighted by the following formula, which is another computing formula of the LPRS, which is obtained through the use of the Fourier series. So this is the infinite sum of the real parts and infinite sum of the imaginary parts at multiple frequencies. If we disregard all the terms except for the first one, we will get the Nyquist plot. So now, if we have the LPRS, if we compute it as was shown by using one of these formulas, then we can simply find the periodic motions in our system as the point of intersection of the LPRS and of this straight line. And we can also find the equivalent gain through finding the real part at this point, real part of the LPRS at this point of intersection. And for analysis of the force motions or analysis of the average motions, we simply replace the relay with the equivalent gain that we find by using the LPRS method. And this is our model for analysis of average motions that can be used for analysis of either a variable set point or variable disturbance that can be applied here. Here a few slides that give examples of LPRS for first order dynamics with its plot, second order dynamics for different damping values, integrating second order dynamics, double integrated, third order dynamics. These are the formulas of some low order dynamics. What can we note about this? We can note that it's for the invertible matrix A, it starts at a very specific point, because Ca to the power minus 1b is the negative value of the DC gain of the system. So it will start, if this DC gain is 1, for example, which will be the coefficient in the transfer function, then it will start at the point of 0.5 minus j pi over 4, which was shown here, for example. This is 0.5 minus pi over 4 for the imaginary part. And for the final value, we can see that it arrives at the origin in the complex plane. If our transfer function, if our linear system doesn't contain delay, if it has delay, so we will have a different situation in this case. Also, what is remarkable is that the high frequency asymptote of the LPRS is similar to the high frequency asymptote of the Nyquist plot, so which is a very useful property for us. So now about LPRS analysis of the sliding mode control systems. So what do we have? We have a certain plant here, and we have a sliding manifold. We design a sliding manifold using all these states, and as a result, the dynamics from this signal UA to sigma has the relative degree of 1. So that if we disregard what is given in red here, we will have LPRS of the system that has relative degree of 1, and we don't have the point of intersection with the real axis. We have an ideal sliding mode. So if we add dynamics of the sensors and actuators that will be in series with all these dynamics, we will increase the relative degree, and as we saw before, now our LPRS would have a point of intersection with the real axis, and we will have chattering, but besides, like what is shown here for higher relative degree, we will have this point of intersection, we will have finite frequency oscillations, but besides, we will also have some finite value of Kn that was infinite if the relative degree of the plant is 1, because it was here. It didn't have any point of intersection with the real axis except for the origin. So now we have the equations of the original systems and equations of the average motions when we introduce the equivalent gain in the system. So these are our equations of the average motions in the system. What is the relationship between now what we have found through the LPRS with the additional dynamics present and without additional dynamics? The difference is Kn, which the difference is through Kn. So if in those equations that are on the left-hand side, Kn approaches infinity, then the last two equations simply transform into Sx0 equals to 0, and U0 becomes U equivalent. And the equivalent control can be also found from the reduced order dynamics. So, and on the right-hand side, we have the reduced order dynamics of the system, which describes the motion in the ideal sliding mode control system, and on the left-hand side, in the real sliding mode control system, the average motions. So, what is chattering? So, let me summarize. Chattering is high-frequency oscillations in a sliding mode control system which occur because of the combination of two factors. This is the presence of Lipschitz discontinuous nonlinearities and additional dynamics. Not one of them, but two of them. So two factors must be present, and they are always, both are present in all real control systems. So as a result, chattering is unavoidable. Chattering occurs in all parts of the system, in output signal, sliding variable, control signal, actuator signal. So that's why it is necessary to look at all the signals to assess the effect of chattering. Chattering is unavoidable, so as I said. And LPRS, or describing function methods, can be used for analysis of chattering. And for the analysis of closed loop performance, equivalent gain through which we analyze this closed loop performance is given by this formula, and it becomes infinity once we remove the additional dynamics. So if we don't remove the additional dynamics, Kn becomes finite value, and we don't have an ideal disturbance rejection, which is shown by this model below. So it's a real sliding mode control system, cannot ensure ideal rejection of external disturbances. So this notion can only be applied to ideal sliding mode. In real sliding mode, this doesn't happen. And to illustrate a very, very brief example of boost converter, I should give credit to my student Ayman Al-Zawaideh, who was working on on that. So this is one of the successful applications of the sliding mode control in power converters. So first, we need to, in analysis, we need to transform these equations into equations of the relay control system if we would like to use the LPRS analysis for that. So which is done through transformation that was shown in the previous slides. And the linearized model of the plant, because the plant is not quite linear, so it has some nonlinear components that we need to disregard. So the linearized model of the converter is given by the following formulas. We find this is the blue line is the LPRS, the red line is the line pi b over 4c, the intersection of which we look for. And what is remarkable here, it was also implemented, that it indeed doesn't reject external disturbances. We applied an external disturbance in the form of the fluctuating source voltage. And we can see that we have chattering, which is like thick red line, but we also have fluctuations with 100 Hertz because it was a rectified 50 Hertz signal coming from the source, from the voltage source. And this is exactly described by the LPRS method, like due to the limitations of time, I'm not going into the details. You can find this is in our publication, those who are interested. So the details of this analysis. And the conclusions. Sliding mode control system is a special type of relay feedback system. Its principal dynamics has relative degree of 1, and the relay in this sliding mode control system has no hysteresis. The presence of actuators and sensors adds relative degree. So this leads to chattering and non-ideal closed loop performance. Analysis can be done through describing function and LPRS methods. And as a result, suitable applications of sliding mode control are those that tolerate chattering, power converters, observers, and possibly some other systems that can be found, but those two are definitely currently are the most successful applications of the sliding mode control. And for further readings, I recommend my book, which is titled Discontinuous Control System. It's about the LPRS method, and recent publications on the phase deficit, for those who are interested, is given here. It was just recently published in International Journal of Robust and Nonlinear Control. Thank you very much for listening, and I welcome your questions now. Okay, so thank you, very useful. I don't see any questions. I see just wishes of good afternoon to me. Thank you very much, and good afternoon to everybody of you. And I also see some familiar names here in this correspondence. But I welcome your questions. Are they? No. No questions. No questions. Let me thank you, everybody who came to this lecture. It's my pleasure to give it to you, to share my knowledge, and to share my thoughts about what I think about this very challenging and not always clear subject in the control theory. Thank you very much.
Doctor, there's a few questions just coming.
Coming?
Yeah.
Questions? Oh, okay. Mm-hmm. Just 1 second, I almost, yeah. Okay, there was a question whether it would be possible to use this method on TSM, I think, TSMC. I understand that this is about terminal sliding mode control, if I interpret this abbreviation correctly. Yes, I believe so. I believe so. I also understand, my understanding that the question applies to the LPRS method. It would be possible because the output of the terminal sliding mode, terminal sliding mode. Yes, it would be possible. It would be possible. The output of the sliding mode in terminal sliding mode control is still a Billy feedback control. So although we can interpret it as a nonlinear sliding surface. Nonlinear sliding surface. So instead of the equations for the sliding variable that we had it sigma equals to Sx. Instead of that, we will have nonlinear dependence. Of course, it requires some, let's say, exercise on the LPRS derivation itself. But if you please look at the book that I mentioned, there are some examples of the use of the LPRS for nonlinear plants. So here we come to the situation of having an LPRS for a nonlinear plant. So this is still possible. However, we cannot directly use the formulas that I presented. Okay, use this technique in nonlinear sliding surfaces. Yeah, I think I have answered this question. Is it possible to use this technique on terminal sliding mode control and nonlinear sliding surfaces? I think we can present the terminal sliding mode control as a relay control and a nonlinear sliding surface. So that's exactly what I was talking about. To investigate nonlinear dynamic system, could you suggest some other application except the electrical systems? Theoretically, you can try it everywhere. You can try it everywhere on, let's say, in mechanical systems. But in mechanical systems, you would have chattering that will be expressed as vibrations. So, if your mechanical system can tolerate these vibrations, it may be all right. But I think there are more applications that I just mentioned. But the main obstacle here is chattering, of course. The second drawback that I mentioned, which is non-ideal closed-loop performance. Yes, there is a deterioration of closed-loop performance, but we have it for every system. We don't have chattering for every system. So that's why we need to find systems or applications which can tolerate chattering from this point of view. How the chattering can be explained when this is multiple time Biel axis crossing over LPRS plot in real control system. Okay. This is also possible. I know some examples when let's say even two different frequencies of self-excited oscillations can be produced in the actual system. But usually when we have multiple crossings, to have it as chattering, we need to have orbitally stable oscillations. So oscillations can be revealed in the actual system only when they are orbitally stable. Usually when we have, let's consider a relay feedback system, which is a structure for the sliding mode control. When we have an intersection from below to above, usually it gives us a stable, an orbitally stable periodic solution. When we have a crossing from above to below, usually it gives us unstable periodic solution. For example, if we have only one crossing from below to above and one crossing from above to below of the Biel axis, obviously only one solution is stable and this will produce chattering. But if we have let's say two crossings from below, then everything will depend on where our initial point would be. So we may come from one periodic solution or to one periodic solution or to a different periodic solution, and both may be stable. Such situations are also possible. However, I believe they're quite rare. So basically I don't consider them here in this presentation. Okay, thank you very much again, and have a good rest of the day. Thank you for coming here and listening to this presentation. It is my pleasure.